Binomial distribution part 1. Let's go back to our experimental setup where we played a game with 2 red and 1 blue balls. You saw that by asking people to choose 4 balls from the bag, we were able to evaluate the probability and conclude that our strategy would not be profitable in the long run. But what if you want to evaluate profitability of other combinations like 2 red balls and 3 blue balls, 1 red ball and 4 blue balls? Is there a way we can generalize these experiments? Let's go through a very commonly occurring and useful probability distribution, the binomial distribution. Using the same red and blue ball example, we'll see how such problems can be generalized and solved using binomial distributions. Let's start with some simple questions. Suppose you don't have the resources to conduct the experiment where people draw 4 balls from a bag containing 2 red and 1 blue ball. Can you still find out the probability of getting 1, 2 or 3 red balls? Let us try it out. Now since there are 2 red balls and 1 blue ball in the bag, the probability of getting a red ball in one trial is 2 by 3 and the probability of getting a blue ball is 1 by 3. Suppose you are drawing 4 balls from the bag. Can you tell us the probability of getting a red ball each time? Remember that the multiplication rule states that the probability of event 1 and event 2 happening if they are independent is equal to probability of event 1 into probability of event 2. Here we have 4 events taking place as we are drawing 4 red balls. Hence, the probability of all these 4 events taking place is going to probability of event 1 into probability of event 2 into probability of event 3 and into probability of event 4. According to the multiplication rule of probability, the probability of getting 4 red balls after 4 trials equal to probability of getting a red ball in the first trial into probability of getting a red ball in the second trial into probability of getting a red ball in the third trial into probability of getting a red ball in the fourth trial, which is equal to 2 by 3 into 2 by 3 into 2 by 3 into 2 by 3 equal to 0.197. Remember that we are replacing the red ball again after drawing it. Now suppose we denote the event of drawing a red ball as uppercase R and the event of drawing a blue ball as uppercase B, then the combination of getting all 4 red balls will be 4 times R. Now let us consider another possible scenario where the sequence of drawing the balls is B times B and triple R. This means you drew a blue ball in the first trial and red balls in the remaining 3 trials. What would be the probability in this case? Once again, applying the multiplication rule to calculate the probability, we would get the probability as probability of drawing a blue ball, which would be 1 by 3 times. Probability of drawing a red ball would be 2 by 3 times. Probability of drawing a red ball, which would be again 2 by 3 times probability of drawing a red ball. And this would be equal to 1 by 3 into 2 by 3 into 2 by 3 into 2 by 3 equal to 0.0987. Remember that 1 by 3rd is the probability of getting a blue ball in one trial and 2 by 3 is the probability of getting a red ball in one trial. Similarly, there are various combinations in which we can get 3 red balls and 1 blue ball. Here the first ball was blue followed by 3 red balls, but we can also have a combination where the red ball is blue and the first, third and fourth balls are red and so on. If we write down the different sequences in which we get 3 red balls and 1 blue ball, then there are 4 such sequences, that is B triple R, R B double R, double R B R and triple R B. If you calculate the probability for each of these events, you will see that all the 4 sequences have the same probability of occurring, that is 0.0987. So the probability of getting a combination which has 3 red balls and 1 blue ball is equal to 0.0987 plus 0.0987 plus 0.0987, that is 4 times 0.0987, which is equal to 0.3948. Notice that we are using the additional rule here. The addition rule states that the probability of 2 events happening, that is event 1 or event 2 happening if they are independent, is equal to probability of event 1 plus probability of event 2. Here we use the addition rule for 4 independent events and that is how we got 4 times 0.0987 equal to 0.3948. Now we'll move on to the second part of binomial distribution. As you may recall, we can find the probability of x equal to 1. There are 4 possible combinations for x equal to 1, namely the first ball being red and the remaining 3 being blue, or the second ball being red and the remaining 3 being blue, and so on. Let's consider the case where the first ball is red and the other 3 are blue. We can compute the probability of this outcome as 2 by 3 as the probability for the red ball times 1 by 3 as the probability for the first blue ball times 1 by 3 again as the probability for the second blue ball times 1 by 3. That is the probability for the third blue ball. The product of all these will give us the probability of this outcome of the first red ball followed by 3 blue balls. The product is the value 0.0247. Since there are 4 such outcomes with 1 red ball, essentially giving us the outcome of 1 red ball as 4 times 0.247, which comes to 0.0988. Similarly, we can compute the probabilities of getting 0, 2 or 4 red balls in the same way. Let's try to generalize this probability. Let's say that the probability of getting a red ball in one trial is not 2 by 3 but p. What would be the probabilities in that case? Again, p is the probability of getting a red ball. The probability of getting 4 red balls is in 4 trials is equal to p to the power 4. Similarly, since there are 4 combinations in which we can get 3 red balls, the probability for x equal to 3 is 4 times p to the power 3 into 1 minus p. Why did we get this 1 minus p? 1 minus p represents the probability that we are getting a blue ball, so we evaluate this expression as 4p to the power 3 into 1 minus p. The probability that the random variable will take the value 0 is given as 1 minus p to the power 4. Why so? This is because 0 red balls means there are 4 blue balls and each blue ball has a probability of 1 minus p. Thus, it is 1 minus p times 1 minus p times 1 minus p and so on up till 1 minus p to the power 4. Probability of taking the value 1 for our random variable is 4 into p into 1 minus p. Again, this is because there are 4 combinations where we can have 1 red ball and 3 blue balls. The probability of x equal to 2 is 6 p to the power 2 into 1 minus p to the power 2. For x equal to 3, we had seen this earlier as 4p to the power 3 into 1 minus p. Again, for x equal to 4, it is just p to the power 4. So now let's extend this case to a more generic case where instead of 4 times, we were to draw the ball n times. Instead of having probability as 2 by 3 for the red ball, let's keep it generic at a value of p. And instead of having 1 red ball or 2 red balls, let's generically say that we want to find the probability of getting r red balls from the back. Let's see how we can calculate for p x equal to r, that is probability that x equal to r. We would have to get r red balls and n minus r blue balls. So the probability of getting one such combination is equal to p into p and so on up to r, that is p to the power r, multiplied by 1 minus p into 1 minus p and so on up to n minus r times, which is equal to p to the power r into 1 minus p to the power n minus r. Finally, let us see how we can generalize the multiplication factor. You recall this factor was calculating the number of combinations of getting r red balls out of the n total balls. For example, when we selected one red ball out of 4 balls, we say that there were 4 different combinations in which this was possible. When we were drawing 2 red balls out of 4 balls, we saw that there were 6 different combinations that would generate. So if we have to generalize this, we can count the number of combinations in which we can get r red balls out of a total number of n balls, and this will be equal to c, NCR. Hence, the probability of getting r red balls after n trials is equal to NCR p to the power r into 1 minus p to the power n minus r. Using this formula for each value of r, that is 0, 1, 2, 3 till n, we can find the probability distribution of our random variable x. For example, for p x equal to 0 would be equal to nc0 p to the power 0 into 1 minus p raised to the power n. Px equal to 1 would be equal to nc1 p1 1 minus p raised to the power n minus 1, and so on up till p x equal to r would be equal to ncr p to the power r into 1 minus p raised to the power n minus r. This probability distribution is called the binomial probability distribution. Let us now understand under what conditions we can use the binomial distribution. First, the total number of trials must be fixed at n. In our example, every participant got exactly 4 chances to pick out balls from the bag, so n is equal to 4 here. The second condition is that each trial is binary in nature, which means that it has only 2 possible outcomes, success or failure. Going back to our example, there were only 2 possible outcomes that could take place when the participant tried to take out a ball. The first possibility is that he picks a red ball, and the second possibility is that he does not pick a red ball. The third and final condition is that the probability of success is the same in all trials, denoted by p. In our case, the probability of success when picking a red ball is always constant and equal to 2 by 3. Suppose we had taken the same scenario and had not been replacing the red ball after picking it out the first time, then the probability would change when the participant would try to pick the second red ball. In that case, we would not be able to apply the binomial distribution. When all of these conditions are satisfied, then the random variable will follow a binomial distribution, and the probability for x equal to r, that is getting r successes in n trials, can be calculated as NCR p to the power r into 1 minus p raised to the power n minus r, as given by the binomial distribution. This is a very commonly observed type of probability distribution among discrete random variables. It is seen in conditions with binary results. Binomial probability distribution, expected value, and standard deviation. Remember that in our earlier experiment, which we conducted with 100 participants, we estimated that we can expect a person to draw 2.64 red balls in one game. This value 2.64 is nothing but the expected value of the number of red balls for each individual. Recall that the expected value is nothing but the average value that we would expect to get from a random variable, and the way it is calculated is that we take the value that x takes x1 multiplied by the probability of that x takes x1 summed up for all the values of x that we can take. So basically it is x1 times probability of x1 plus x2 times probability of x2 and so on up till xn times probability of xn. Can we generalize this calculation of expected value and variance for the binomial distribution? Of course we can. While the derivation of this formula is beyond the scope of the discussion, for any random variable that is known to follow a binomial distribution, we can compute the expected value and variance using these general formulas. The expected value of x will be n times p, where n is the number of trials and p is the probability of success. Then we have variance, which is equal to np times 1 minus p. So let's take our example of calculating the number of red balls and calculate the expected value and variance. Remember that in any experiment, the participant was allowed to draw 4 balls. So how many red balls on average can we expect participant to draw? The answer will be n times p, where n is equal to 4 and p is equal to 2 by 3, as that is the probability of getting a red ball. Multiplying both these values, we get 4 times 2 by 3, which is 2.67. This means on average we can expect a participant to draw 2.67 red balls in a game. Similarly, we can calculate the variance of this random variable x. This would be n times p times 1 minus p. That is going to be 4 times 2 by 3 into 1 by 3, which is equal to 0.88. You saw that using the binomial distribution, we were able to calculate the probability of getting an exact value. For example, if we want to know the probability of x equal to 4, that is 4 red balls, we know the formula, that is 4c4 2 by 3 raised to the power 4 into 1 by 3 raised to the power 0, which is equal to 0.1975. But what would you do if you wanted to calculate the probability of getting less than equal to 3 red balls? Therefore, we are calculating the probability that x can take values 0, 1, 2, 3. We can say that this value is simply calculated as probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3. We can substitute these values and we'll find that is equal to 0.1235 plus 0.9877 plus 0.2963 plus 0.395, which is equal to 0.8024. Thus, there is an 80.2% chance that any randomly selected participant will have selected at max 3 red balls while drawing 4 balls. These kind of probabilities are very frequently calculated in real life. So any probability where we have to determine the likelihood of x being less than a certain number is called cumulative probability. For example, 0.802 is the cumulative probability for x less than equal to 3. And instead of saying probability p of x less than 3 is 80.2%, we can use f of x equal to 3, that is 0.802, where f represents the cumulative probability. Similarly, we can calculate the cumulative probability for each value of x and create a table as shown here. On the screen here, you can see the probability distribution table that we had originally created. Using this, we can see how to create cumulative probability table. For x equal to 0, the cumulative probability will be probability of x less than equal to 0. Since for x less than equal to 0, x can take only one value, which is 0. The cumulative probability here will be same as probability of x equal to 0, which is 0.01235. Next, let's calculate f of x equal to 1, where f of x equal to 1 means probability of x less than equal to 1, which will be probability of x equal to 0 plus probability of x equal to 1, which will turn out to be 0.11. Similarly, we have f of x equal to 2, which will be probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. Now, we already know that probability of x equal to 0 plus probability of x equal to 1 is, as this is the same as probability of f of x equal to 1. Thus, we can write f of x equal to 2 as f of x equal to 1 plus p of x equal to 2. We know that f of x equal to 1 as 0.11, and we know that probability of x equal to 2 is 0.296. Hence, f of x equal to 2 will be 0.111 plus 0.2963, which is equal to 0.4074. Similarly, f of x equal to 3 will be 0.4074 plus 0.39506, which is equal to 80.247% or 0.80247. And f of x equal to 4 will be f of x equal to 3 plus probability of x equal to 4, which is 0.80247 plus 0.1975, which is equal to 1. This is because f of x equal to 4 means that we are finding the probability that out of 4 balls drawn, 4 or less could be red balls. This will always be true as the number of red balls can never be more than 4 if the maximum balls that we are drawing is 4. Hence, the final value in the cumulative distribution table will always be 1.